Hi students, Angus here, and we're back for part 2 in our chapter 12, the Introduction to ANOVA, or Analysis of Variance. Today we're going to go over the logic of ANOVA and some of the annotations or notations, the symbols we're going to need to begin doing ANOVA, to test for differences between 3 or more groups. First, we're going to look at the logic of ANOVA. And remember the F ratio. Take a moment and review your notes to see if you can find or if you can remember what the F ratio is. If you're seeing this slide and it brings back some memories, yes, it should. F here is between treatment's variance over within treatment's variance. So a bit more details about these types of variances. Between treatment variance is the variability that comes from differences between groups. So general differences here reads differences between treatment conditions. So remember the factors we had for types of therapy and the time that they were tested, either before the therapy, after the therapy, or 6 months after the therapy. And you can look back on the previous slides in the last parts of the video to think about what the differences between groups are. Also, between group variance, it measures the differences among sample means. Again, because we're measuring the groups with some type of score, once we group the scores together within the groups, each group has its own sample mean, and we are comparing those means. This time with ANOVA, we're looking at the variances between those means, and that's between treatment variance. The denominator of the F ratio, the thing we want to put in the bottom of the fraction, is within treatment variance. In this case, within treatment variance is the variability within each sample. So remember, while we're looking at differences between groups for between treatment variance, for within treatment variance, we're looking at variability within the groups. Therefore, here, one thing you should note in the slides is that the last sentence that says individual scores are not the same within each sample. That means the scores themselves individually, when you compare one with another, even if they're in the same group, they're going to be different. So that's within groups or within treatments variance. So one way to show this graphically, and I'm going to continue writing on this whiteboard here, and we're done with the experiment-wise alpha. I may have to start a new whiteboard. So there you go. That works just fine. So remember the F ratio for a moment. It's between groups or treatments variance over within groups variance. And this is what we're going to work with. Now, what does that look like, without using words? So here's a way of explaining it. I'm going to draw a big chart with 2 axes here. Okay. So let's say one of these is, what we measure, within, if it was a therapy and the therapy was measuring, let's say, stress levels. So let's say this is the stress levels. And then here for the stress level, obviously, the higher the stress level, the worse it is. We generally don't like too much stress. For the x-axis here, we may consider something like, oh, okay, well, we can have the time of measurement. That is, thinking back to the example, okay, well, when are we going to measure or assess the participants in the stress level after the therapy? So, remember, we had distributions like this before, these normal distributions for each sample and populations too. So each one has its own mean and has its own distribution. It can be a sample mean or population mean. So this one's the population, for example, and this one's the sample. Okay, and since we're comparing between samples, there are two ways of me drawing this. So, for example, over here is 6 months later. Okay, I'll make that this way. And then here is after therapy. And then here is before therapy. Now, you may notice that we're measuring stress level. So we're going to actually flip these distributions and rotate them clockwise 90 degrees. So they start to look like this. So here's what they would look like. And I'm going to use these to show you. So again, we're measuring stress levels, and imagine there's different types of stress levels and different levels of stress level. So there are two groups for before therapy, right? So maybe therapy 1, and I think I need to use a different color here. So I'm going to use calming blue for therapy 1. And I don't know, let's say peaceful green. Sorry, I was right, green. Green, peaceful green for therapy 2. Okay? And this is totally hypothetical, but it is possible. So, for example, we start with therapy 1. And so, before therapy, let's say, okay, they're pretty stressed, so they have their distribution like that here. So you notice that there is already a spread within this particular group. So remember, this is therapy 1 before the therapy, and this is us measuring the stress level. Let's say peaceful green has maybe they started less stress. And I'm just drawing them apart just so it's easier for us to see them. And also, the green group, therapy 2, has its own spread and has its own sort of distribution. Sometimes the groups could overlap. So maybe they're very close together like this. And again, it has its own spread. But you notice each group has its own distribution and its own spread and its own mean, moving on to the next group. Let's say after therapy, the blue group, yes, it's working. And again, it has its own variance, okay? And also its own spread. And peaceful green, oh, okay. Actually, let's pretend, oh, wait a minute. They actually were more stressed. Uh-oh, that's not good. Maybe there's something wrong with the therapy. But again, we notice that each time you measure and take a sample to measure them, it has its own distribution. One last time. So the third level in the second factor, 6 months later. So what's that going to be like? I have to erase the whole thing like that. There you go. Oh, maybe 6 months later after therapy, oh, well, life gets back on track and there's daily stress again. And so, maybe they go back to baseline. Now, you may know what that means, just going back to normal or what they originally started with. And then somehow for the green group, oh, wait a minute, something clicked for them. The therapy was designed to make them stress at first, and then they have to sort out those things, and then they're less stressed in the long run. And so 6 months later, they actually end up less stressed. So I've drawn the complete picture here. Notice that between groups, they could be different. So I'm going to use this pen. So between groups, if you look at the blue, if I drew a line across all these, you can see that there's some differences between them. So here is for therapy 1, I'm going to use the blue pen again. And this is before therapy, and this is therapy 1, this is after therapy, and then one more time is 6 months after. So you notice there's a bit of a spread between the groups. Likewise, if we did the same for green, I'm just going to put the measurement over here. You may notice that it has its own spread here too. So here, so here's therapy 2. Oh, no, hold on. This is before therapy, and then the one at the top is after therapy, and then the one at the bottom is 6 months after therapy. So you may notice that while we can look at between group variance, that is these arrows here, respectively, and we can even begin to compare between groups, but for now we're sticking with the same factor within the therapy groups. And again, we're going to compare that, the between group variances, with the within group variances. That's here within these particular distributions, like this. See? And so this goes to say, if, for example, all these distributions were really close together, the between group variance would be almost, if not exactly the same as within groups variance. So if, just for the sake of argument, if between group variance happens to be 1 and within group variance also happens to be 1, the idea is that they're the same, then the ratio, the F ratio, is 1. So really, there isn't really a relationship between them, or we could begin to infer that. So that's the logic of ANOVA. We're looking at whether the between group variance, that is, the differences between the distributions, looking at the lines across the graph here, are so much bigger than within group variance, that is the distributions themselves, that you're going to get a larger than 1 F ratio. It could be 2, it could be 3, it could be even 10 or even 100. And if you take a moment to look at your table of F ratios, you could see some of those ratios can get pretty high, even in the thousands or tens of thousands. Again, the larger the F ratio, the greater the between treatment variance, and the more likely or more reasons we have based on statistics evidence that we can say, yeah, there's probably a difference between the groups, or at least a relationship between them. Okay. So the next couple slides look at between and within variance in a bit more detail. Again, by now you would see that the pointers within the next 2 slides, starting with this one, between treatment variance or variability, starts to make sense to you. Here again, it's the systematic differences caused by treatments. Remember those lines across the distributions that show you differences between them. That's between groups variability. Okay. Again, these would not be the unsystematic differences of these, would be individual differences. Again, those are the spreads, like these ones here, the spread itself, or any type of experimental or measurement error that's done by the experimenter themselves. Okay, and here for within treatments, these would be your unsystematic differences. These would be your individual differences. Again, this is the 3rd time of me drawing it. These are your spreads within groups. Again, these could be experiment errors. So what between groups are not? Within group variances, that is. So here's the review of your F ratio. Again, we're trying to see if the differences that includes any treatment effects are large enough or so much greater than the differences with no treatment effects that we can say, yeah, there is enough evidence for me to say that the treatments are working, or at least they do make some sort of relationship, whether it is linear or non-linear, that the samples are, far enough apart from each other that you can say there's a difference. Here is a more graphic way using a schematic to compare between treatment variance within treatment variance. So again, this is our 3rd time looking at it. Total variability has 2 components. So the first component is between treatment variance, and this is what researchers are trying to test, what they're looking for. This is the one that gets, their research published. Within treatment variance, those are your individual differences or random unsystematic factors. Those are the ones that we try to account for. And if you remember in your research methods class, that's why we have lab settings. That's why we try to control as many of these factors as we can, so then we can isolate the treatment effect. Just like we do that with our research methods by creating sort of laboratory or more artificial settings to control those factors, ANOVA tries to isolate or at least find a ratio where if we can systematically or using math detect a large between treatment variance over your within treatment variance, then we can say using ANOVA and the F ratio that, yeah, there's probably a difference between the groups. Haven't figured out what specific differences are, but at least we can say they're far enough apart to say that, well, yeah, they're not all bunched together. They're not all the same. Okay. So we come back at this point to writing the null and alternative hypothesis of ANOVA. Now, you may notice this time, instead of writing means, instead of comparing means to see if they're the same, which from last video we discussed could lead us to some problems, particularly increasing experiment-wise alpha to at least more than 5%. It could be 15. It could even be 100 if you do enough tests. 20 tests if alpha was set at 0.05. So notice here the different way of writing the null and alternative hypothesis now. Here we say that the size of the treatment effect is near 0. In this case, the ratio of F, that is between group variance and within group variance, is 1. That means they're the same. That means, oh, the treatment effects are like almost entirely, if not entirely, accounted for with individual differences as well. Okay, at least that's what the math is showing. The alternative hypothesis then is in many ways simpler, because ANOVA lets us analyze variance and compare the samples simultaneously rather than using t-tests that only let us make pairwise comparison between means. We can say, oh, if the size of the treatment effect is more than 0, then the F ratio itself has to be larger than 1. That is, the between variance is larger than the one within. I'm just using size as a comparison. So yes, if you notice that in the F ratio is larger than 1, then we are going to be more likely to be led to say, yeah, okay, the alternative hypothesis, is something we want to look at, or at least we can reject the null and say, there probably is a relationship between the groups. Okay. The denominator of the F ratio is called the error term. Again, think sampling error or sample error. Again, error here, think of it as variability or spread. Okay. And the measure of variability we're using here is variance. Remember that sum of squares value over, n or n minus 1? Yeah, that's the one. Okay. So we'll end our section 1 of part 2 with 2 learning check questions. So take a moment and answer these in your own time. You can pause the video if you want. I'll just ask the questions first. You think about it, write down your answers, and it's important for you to write down your answers as you take notes on this. And then as we go through the answers, compare your answers with the answer. You could look ahead if you want, but the important thing is for you to actually go through the process and think about it. So here we go. Question 1. 1A. ANOVA allows researchers to compare several treatment conditions without conducting several hypothesis tests. True or false? And B is, if the null hypothesis is true, then the F ratio for ANOVA is expected, on average, to have a value of 0. True or false? You can pause the video now if you like, if you're following along in real time while watching this, and write down your answers. Okay, here we go. Well, for the first one, it's true. ANOVA does allow researchers to compare several treatment conditions at once without doing multiple hypothesis tests. That's the reason we have it. One moment. Aha. We're back. Okay. I forgot to let me do the pen writing. So yes, it lets us do several conditions at once. Again, ANOVA is not multiple t-tests. For B, remember, for us to say and fail to reject the null, or if the null happens to be true, that there is no difference, the ratio between treatment variance and within treatment variance would be the same, and therefore would actually be 1, not 0. Okay. So that's it for today. For part 2, section 1. So we'll continue with section 2 in the next video, going over the notations and formulas of ANOVA. Okay, so take a moment, think about what you've just learned, write down any questions you have. Again, you can share them in your chapter discussion thread or email me with the questions directly, or use Canvas Messenger. We'll see you in the next one.